Okay, now let's see how the eigenvalue eigenvector system can be applied to our ordinary differential equations. Okay, so let's try to solve a case which is x dot equals to a x. Okay, this x dot meaning that this is a differentiate by the time. So we use x dot will be equals to a system matrix A times the x itself. And we want to solve, of course, x here. And let's try a simple case, which is uncoupled system. Dynamic system. Okay, uncoupled dynamic system. And you have this basically d over dt differentiate as function of time of x1, x2, x3, to xn. So this is your system. Vector x differentiate by time. And that is equals to uncoupled means the x1, x2, or x3 to xn, they are not influencing each other. So that the coefficients won't influence each other. That means we will have a diagonal matrix. So x lambda 1, lambda 2, lambda 3, to lambda n. And all the other side will be 0. This will be 0. Okay. And this is a diagonal matrix. And times itself, x1, x2, to xn. And you can see that basically the x1 differentiate with time will be equals to lambda x1. And it won't be related to x2 to xn. So we call it uncoupled dynamic system, which is very simple. So x1 dot will be equals to lambda x1. x2 dot will be equals to lambda x2, 1, 2, until xn dot will be equals to lambda n xn. Okay, and you know that this is ordinary differential equations with constant coefficients, so that the solution format will look like exponential. So our solution will be look like xt or nt will be e to the lambda n t to x to some constant c n, some constant. And this constant will be decided by the conditions of whatever. It can be initial value conditions, it can be boundary value conditions. So if we give an initial condition, basically at time equals to 0, you will have x1, 0, x2, 0, until xn 0 for this nth order ODE, right? So you will have n conditions to make sure you x1, x2 until xn. Then our final solution will look like x1t equals to e to the lambda 1t. Cn will be just x1, 0, because e to the lambda n t equals to 0, then this will be just the 1, so that x1t equals e to the lambda 1t, x1t. x2t will be equals to e to the lambda 2t, x2, 0, until you have xnt will be e to the lambda nt, xn, 0. Okay? And you can rewrite this solution format to be a matrices where you have x1t, x2t, until xnt will be equals to, okay, e to the lambda 1t, e to the lambda 2t, until e to the lambda nt times, so all this part will be 0. This is a diagonal matrices because they are uncoupled. They are now influencing each other from x1 to xn. So that this part will be u initial condition x1 0, x2 0, to xn 0. Okay. Then the final solution for this uncoupled system will be x. This is a 1D vector, xt, will be e to the, this matrices, the diagonal matrices, we can say a, t, x, 0. And you know this A is a diagonal matrices for this system because they are uncoupled, okay? So that is one of the using matrices to represent the ordinary differential equations. Then our next question is that, you know, this A is uncoupled system here. So this is a diagonal matrices. What if they are coupled? Then things can be complicated. Can we use eigenvalue and eigenvectors to simplify our coupled dynamics to be uncoupled dynamics? Okay.